Welcome to lesson 3.1. We're talking about functions, domain, and range. So obviously we're going to have some vocabulary to define here. Today's lesson is very light on any algebra or solving skills, but it's very conceptual. And the domain and range are very important. Function is something we should get to a point we can just eyeball if we have a graph, but let's discuss some of these things. So a relation basically just pairs inputs with outputs. And oftentimes in math, when we write equations so that x is the input, the number we plug in, and y is what we want to find out, the output. Functions get a slightly more specific rule. Each input only has one output. Okay, so an example of a function would be any y equals mx plus b graph. All right, so if I have numbers for m and b, this is basically just a relationship where I can plug in an x value and find a y result or output. So the idea of a function, I like to use like a soda machine as an example. A function is like a well-working soda machine. I have my buttons down the side. All right. So when I throw my money in there and I hit, let's say this is like Mountain Dew. So this is Dew, this is Pepsi. It's okay to have a second Mountain Dew button. And then let's say we got a Sprite. I don't know. Heck, that's not even a Pepsi product. Whatever, it's just an example. What do you expect to come out of the machine when I hit the Mountain Dew button every time I hit it? The obvious answer should be always a Mountain Dew. Same thing with Pepsi. I should always get a Pepsi. Okay, it's okay to have a second Mountain Dew button that also gives a Mountain Dew. What's not okay, what would be bad for us, what would make something not a function, is if it was not reliable like this. So if I press the Mountain Dew button twice, not a function would be if I press the Mountain Dew button twice and I get a Pepsi once and then a Mountain Dew. At least if I always get Pepsi, I know it's just something wrong. But if I get Pepsis and Mountain Dews just from pressing this button, so it doesn't matter if one is more frequent than the other. It just cannot happen. All right, this is a bad soda machine if I can't rely on what button I'm pressing. Now, a fun little story, there was a store I was at once that had a random button. But even that random button, it was all preloaded cans. It was always pulling from the same like part of the machine. It has like cans layered that like slide down. It's that was still, it was intentionally random, but it was always pulling from the same slot. So most things we do are meant to be reliable results. Most things in life we'd consider functions. Usually when things aren't functions, it's because there's randomness involved. All right, randomness or some other weird sort of situation. We really try to avoid not having functions. Functions are important because they're reliable. If I press the Mountain Dew button, I should know I'm going to get a Mountain Dew. That's the idea here. So we'll look at what that can be represented as in a table, a picture, an actual XY coordinate grid. So before I write out the first example, this is something we need to know. X is the inputs and Y is the outputs. So the kind of rule here is that we can't have 2 points where X is the same and Y is different. These are the rules to our game right now. All right. So what you're looking for when you have a table or a list of points and it asks you whether or not it's a function, you're looking for any points where the X values match. Then you got to check the Y values. It's okay if the Y values match, but it is not a function if the Y values are different in that case. So let's list out some points and see if we can decide. So we got our rules laid out. All right, so first problem, we've got -2, 2. Try to look for a bad example when it happens. -1, 2, 0, 2, 1, 0, 2, 0. So the rules to our game: we can't have x values that match and y values that don't. Are there any other -2's in the x spots? No, 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 no. Are there any other -1's? No, no, no. Are there any other 0's? No, no. Any other 1's? Nope. So since there are no matching x values, in this situation, it's always going to be a function. It's a function. Yay. Next problem. It's going to look very, very similar. Now we've got 4, 0, 8, 7, 6, 4, 4, 3, and 5, 2. So let's look. Do I have any other 4's? No, no, yes. Do the y values match? 0 and 3? Nope. So our reasoning here is same input, different output. So they were both 4's, but they had different y values. So it is not a function. Okay, so that's kind of how we play this is it a function game. So let's look at it as a table. Same rules apply. We're still playing the same function game. No other -2's, no other -1's. We do have 2 zeros. So we got to check the y's. If the y's match, we're okay, but these don't. Same input, different outputs. Not a function. Okay, there's one more graphical way to look at this before we get into the graphing. This little grouping, this little set kind of thing where x is the set of these 3 numbers, y is the set of these numbers. When you see this, there'll often be arrows pointing from x values to y values. So my question is, in this situation, is it okay that 3 and 11 both point to 15? The rule is, remember, for our game, we can't have one input with different outputs. Okay? It's okay for 2 different inputs to go to the same output, but it would not be okay for me to say, have a split at the 3 where there's 2 arrows coming from it to different things. It's okay to point to the same y value from different inputs. It is not okay to have one input point to 2 different y values. I'm supposed to be able to predict when I plug in an x what my answer is going to be. And if I have it pointing to 2 different answers, how am I supposed to know which one's right? So this is a function because each input has its own output, even if the outputs match. Okay, outputs matching is never an issue for functions. This is a function. It's okay for outputs to match. That is not a problem. We have trigonometry functions that go like this. All right, trigonometry functions are harmonic or sinusoidal, weird words, but there's a lot of points. Everything across this line, that's 1, 2, 3, 4, 5, it goes on forever. That's okay, that is a function. What's not a function is if something doubles back on itself. All right, so we're about to talk about something called the horizontal line test and the vertical line test for a graph. So this graphic right here represents the vertical line test. Okay, now the vertical line test is not an official math thing. It is just a graphical way of following the rules to our game. I know I keep calling it a game, but it's because we're looking for certain things and trying to make a decision. Okay, so this vertical line test is a strategy. So when you actually have a graph, what you can do is use the vertical line test, because this vertical line checks all x values on the line. All right, so let's just say this is x equals 6. It checks all of the results for x equals 6. And the idea is x equals 6 should only have one result. And it's right there. So if we slide this vertical line, the idea is it should never cross the graph twice or more than twice. It should only ever be able to cross once. Not crossing is also okay. Less common, but it's also okay. All right. Here, it does cross twice. So if we say this is x equals 6, these are two y values. So this could be like 6 comma 2 and 6 comma 4. And if I write points out like that for you, on an actual graph, you might be able to identify the specific points. This is just an example, but that's two inputs with different outputs. How am I supposed to know which one of these is right? So yeah, that's a graph, but it's not a graph we like. We like functions because they're predictable. We don't like graphs like this because they're not predictable. What do I get when I plug 6 in? I don't know. Literally, we can't know. That's the problem with this. If there's two possible answers for one input, it's like not knowing whether I'm going to get a Pepsi or a Mountain Dew from the soda machine. What do I keep wasting $1.25 until I get the one I want? That doesn't make me happy. Functions should make us happy in math. This should not. So when we're working in these graphics environments, graphing things with x and y points, we often discuss domain and range. Domain is all possible x values, and for many of the functions we actually use in this class, domain is going to be all real numbers. Not always, but very commonly, because most of the time we're okay plugging in any x value we want to. Range, especially when we get into second semester, will be more limited. Okay, but for this unit, it's all about just being able to play with those ideas. So domain is listing out all of the possible x values, range is all of the possible y values. So I'm going to show a couple graphs, and I'm going to give you strategies for those graphs. The first type of graph is called discrete. Discrete means individual points. So when you see a graph that's individual points, what I want you to do is literally just write out the ordered pairs. So this is -3, 2. Sorry, -2. This is -1, 0. This is 1, 2. And this is 3, 4. Okay, so your domain is the list of all of the x values. -3, -1, 1, and 3. So oftentimes we will write this list inside of this pair of braces. Range is the same thing, but we list the y values. -2, 0, 2, and 4. That is a discrete graph. Individual points, no connected line. All right, let's look at a continuous one that has a connected line. So here's a continuous graph. Continuous is connected. There's a line throughout the graph connecting all the points. Okay. For continuous, we actually write our answer with inequalities, a bunch of and inequalities. So let's start with our domain. We're going to contain all of the x values like it's on a number line. So I'm going to draw some dashed lines at the farthest left and farthest right points. Now, if you ever see an arrow on one of these, like if I had an arrow right here, that means it continues that way forever. You can't draw a dashed line. There's no limit. So instead of being an and inequality, it would just be a simple inequality that says x is greater than or equal to whatever the minimum was. Okay, but try and bear with me here. We're trying to cut off our x values. So how far left can we go on the graph? 1, 2. 2 to the left is as far as I go. So x is greater than or equal to 2. These are closed circles, so we're pretty much always going to have or equal to. And then over here, 1, 2, 3. Sorry, this is a -2. I keep forgetting my negatives today. X is less than or equal to 3. So we write that as an and inequality. X is greater than or equal to -2, and x is less than or equal to 3. For range, we do roughly the same thing, but top to bottom. So range, I'm going to use a different color. So we kind of box in our graph. But remember, if there's arrows on the ends of the lines, we can't box it in like this. My graph goes down to -1, so my y is greater than or equal to -1. It goes up from there, and then it goes up 1, 2 for its maximum. Y is less than or equal to 2. So y greater than or equal to -1, and y less than or equal to 2. Another way to do this is we can have whatever the minimum was less than or equal to x less than or equal to the max. So this is the x min, this is the x max. Same thing with y. Min less than or equal to y less than or equal to max. This is the minimum y, -1, and this is the maximum y. Okay, so other ways to write these, I'm going to erase my answers and rewrite them real quick. If I follow that new way I just showed you, and we saw some of these in chapter 2, right? We'd have -2 less than or equal to x less than or equal to 2. Sorry, 3. I was misreading my own work up there. I'm like, that didn't seem right. Then for y, it's -1 less than or equal to y less than or equal to 2. All right, so this or the other way I showed you both represent and inequalities. Choose your favorite. That's all there really is to it. So that's pretty much domain and range right there. Our final conversation, and I promise it'll be a quick one for this, is independent and dependent variables. Okay, so an independent variable is one that really doesn't rely on anything else. So oftentimes in like a sciencey sort of class, we would make the independent variable time, something like time. And then the dependent variable would be something like distance. Okay, so if I'm driving down the road, the amount of time I spend driving, I can't control. I mean, yeah, I can slam on my brakes, but I can't stop time. All right, but the distance I drove can depend on time. It's this weird kind of relationship where you try and find the one that's the easiest to measure and the one that's least in your control. So we usually try and find some sort of determining factor, if that makes sense. So, you know, like age would be a big one. Age would be something that's likely to be an independent variable. And then, I don't know, world record running speed would be the dependent variable. Okay, age is the thing that's easier to measure and is something we have less control over. And then some other piece of information that's a result of that is the dependent variable. So independent variable, when we write our equations, we always use x for the thing that seems the most easy to measure and the thing that's least in our control. Dependent variable is what we want to know as a result of that. Okay, so it's hard to just say whether one's right or wrong because technically you can measure either of them. All right, it's one of those things where it's not really a hard and fast rule. You can choose your own independent and dependent variable when you're doing something like a science experiment. It's just one of them usually makes more sense to be independent. It's usually easier to measure. All right, so that's all the conversation we have on this for today. We'll do a couple example problems together in class, but there we go. Almost kept it under 20 minutes for you guys.